To discuss, we're going to go over the area of a sector of a circle and basically prove that it equals to, well, the area is 1/2 r squared times theta, where r is the radius and theta is the angle here, and this is just a random sector of a circle. And again, this is, if you were to draw a full circle, what I mean by random sector is just any slice of this circle. Just pretend this is a better circle shape like that, and this angle works for any angle in the circle. So for example, if theta is equal to, well, 2 pi in radians is, this is 2 pi radians, which again, like I showed in my earlier videos on radians, this is the same thing as 360 degrees in terms of degrees. So if angle is 2 pi, this one we're going to be dealing with radians always. So we have area is equal to 1/2, then radius squared times it by theta, which is 2 pi, which then the 2's cancel, and you're just equal to pi r squared equals, well, area of a circle, which is the formula we are used to. And there it is. Yeah, and you could learn more about the circle and area of it in my earlier videos, all in the video links below. So as you can see, this works for any angle. And so now the proof of it, well, first of all, we're going to assume, so for the proof, we'll just deal with where the angle theta is less than equal to pi over 2 and greater than or equal to 0. And then later on in the video, I'll show that how the angle could work for pretty much any angle in this circle. So let's draw an xy axis. So x, y, and let's just put this sector in between 0, where the angle's between 0 and pi over 2, or this is, again, that's 90 degrees. So pi over 2 radians is 90 degrees. So in between there, let's just draw a line like this, and then this curves like that. So I'll just actually fill it in. So this is the sector like that. And what we're going to do is look at this sector right here and break it into 2 areas. So put a line across like that. So now we have 2 areas here. One's a triangle and one is this one over here. So this one we'll call this A1. And then this one right here, we'll draw it in blue, we'll call this A2. So now what we first do is, well, this angle across, I'll erase this and I'll draw this. So angle theta, so that's the angle, and the radius is r, is across. So then at this very point is also r right here. So x equals to r, that's the radius of this sector. And now when calculating, well, this length right here, this is the adjacent. So if you recall, cosine by definition is equal to adjacent over hypotenuse, and in this case the hypotenuse is r. So this means that the adjacent length of this triangle is equal to cosine, to solve it for adjacent, then times it by r. So we have here r cosine theta. I just put this r in the front here, doesn't matter. And likewise, by definition, sine theta, and you can see more about these definitions in my earlier videos on trigonometry, we have opposite. So in a right angle triangle like that, opposite over hypotenuse, where hypotenuse is r. So opposite here is equal to sine theta times r. So then that is this length across. I'll draw this like that. So this length is r times sine theta. And now the last bit of information we need to solve it is, well, basically this curve right here, that's an area, I mean, that's an equation of a circle. So that follows that equation of a circle, that curve of a circle. And then, like I showed in my earlier video, the area of a circle is equal to, in this case where the origin here is 0, 0, x squared plus y squared equal to radius squared. So that's the area of a circle where the origin is at the center here, where it's at 0, 0. So if we solve this for y, rearrange it, we have move x on the other side, r squared minus x squared, and then we have I'll just write this. Yeah, I'll write it again. So we have y is equal to, put this here, r squared minus x squared, and then square root it. But you have a plus or minus because whenever you square root, there's a plus or minus. So this is for the bottom side. So if you were to draw, if the angle is across like this, and the sector is like that, etc. But in this case, we're only dealing with the positive side, which is in this this quadrant right here, the positive x and y section. So we'll only deal with the positive one right here. We're not dealing with the negative or the bottom of this sector, of this circle. Yeah, so basically this curve follows the positive of the square root r squared minus x squared. So now the area is going to be a combination of the two. So thus we have area of the sector is equal to A is equal to A1 of the triangle plus A2 of the curved section right here. And we could solve this one pretty easily. So A1 is equal to, well, just as a triangle, like I showed in my earlier video on area of a triangle, is just base times height divided by 2. In this case, the base right here is just r cosine theta, and the height is r sine theta. So we have r cosine theta times r sine theta, all divided by 2. This just equals 2, so we have A1 equals 2r squared. So this r is just multiplying it, just add the power. Yeah, r squared times it by, put the sign in front, sine theta, cosine theta, and then all divided by 2. So we have the first area. Now we look at the second area. So the second area, we could just use an integral where we go, the range is going to be, well, we're integrating, the interval is going to be from this x equals to r cosine theta, that's the length here, and then up to r. So, yeah, so for area 2, we have equals to the integral of r, integral from r cosine theta to r of now the area, or the function of that curve, which is just basically r squared. So square root r squared minus x squared dx. And now in solving this integral, it's not a straightforward one, but what we can do, if you recall my earlier videos on trigonometric substitutions for integrals, so recall trig substitution. Yeah, so right here, trig substitutions for integrals, my earlier videos on these, basically for the expression in the integral, for the expression, so in our case here, so for the expression square root a squared minus x squared in the integral, yeah, we could use the substitution, so can use the substitution or the trig substitution to solve this integral. Yeah, so we can use x equals to a sine theta or x equals to a cosine theta. And the reason we would use this kind of trig substitution is because then you can use, basically we use this substitution, then use the trig identity, use the trig, let me just write this neater, identity. So if you were to use the basic one, sine squared theta plus cos squared theta equals to 1 right here. So rearrange it for whichever case, and then you could use, if you rearrange this for cosine, so you could do cosine theta is equal to, this will be 1 minus and then sine squared theta. Or other way around, you could go sine theta is equal to, just move this around and square root 1 minus cosine squared theta. And since you're square rooting, it'd be plus or minus, and then the plus or minus depends on, but you have to restrict theta to define a one-to-one function. Let's erase this, 1-to-1 function. And again, you could learn more about this in my earlier videos on trig substitution, and also this will make more sense once I evaluate further this area. Yeah, so now if we apply the substitution in our case, what we have, so in our case, yeah, we are already using theta, so that we are using this variable, and we know that, and a is, in our case, a is equal to r, so we could choose any of these x equals a sine theta or a cos theta, and we'll see that in fact if you were to do this later, we're going to using this one is actually easier to solve, but I'll use this one just because it provides a bit more complexity and just more mathematical stuff that's pretty interesting to do. So we'll choose x equals to r sine theta. So instead of using this one, sine u, because we already have this, so we'll pick u instead, and then we have to restrict it so it's a one-to-one function. So we choose u is defined between pi over 2 and 0, so greater than 0, less than equal to pi over 2, because, well, in this case, because x is less than equal to r and greater than equal to 0. So this is positive, i.e. x is positive. And then when you were to graph this out, basically what I mean by one-to-one and why x is positive here, if you were to graph this is x, y, actually this is u. So the graph of sine looks something like this. And then I'll show it further. Yeah, so it goes something like this. And I'm doing a dashed line because that's not the interval we want. So this is sine u. And then at this very top point, this is our pi over 2. So this is plus, and this is negative here. So we're going from here to here, we want the positive side. And if we were to go, let's say, from the interval, if we chose it past this point, let's say here, etc., and then if you use a horizontal line test like I showed before, then we'll have, at one y value, we'll have two x values, where this would be, well, not one-to-one. Not one-to-one. To 1. So we defined u between here, and this is the substitution we'll use. And again, you can learn more about this one-to-one functions and trig substitutions in my earlier videos, all in the video link below in the description. So we use a substitution, let x equals to r sine u. So in this case, when you take the derivative here, d of x is equal to r, and then we have sine u, which is going to be cosine u, and then using chain rule, du. And also with trig substitution, it's usually better to evaluate the indefinite integral and then fill in the variable for x to solve the definite integral. So evaluate, or actually I'll write it better, for trig substitution it's usually better to evaluate the indefinite integral, and this will make more sense as we get through this. Indefinite integral, and then switching back to the x variables, and then solving the definite integral. The definite integral. And again, this will make more sense as I solve this through. So we have the integral of square root, we're doing the indefinite, so indefinite, we're not doing any interval right here, so just the integral of square root r squared minus x squared dx. This equals to, when we plug in our substitution, x equals r sine u. So integral, then we have r squared minus, to plug it in, x squared, that's just going to be r squared, and then times it by sine squared of u, and then the dx is equal to r cosine u du right here. So we have this, and then we could evaluate this or simplify it further. So this square root, we could factor out the r squared, so that will be basically square root r squared, and then 1 minus sine u squared right here. And then again there's this r cosine u du. So in here this r squared square root, that's just equals to r. And now this right here, this equals to, like I showed above, scroll back up, that is just, well, cosine of u squared, but then you're square rooting it. So this 1 minus sine squared, yeah, and then square root, that just becomes cosine theta. This is plus or minus, but we've defined theta to be less than pi over 2, greater than 0, and for cosine that is positive, because cosine looks something like this. This is how cosine looks right here. So this is positive, this is cosine theta, this is theta, and at this point right here is pi over 2, and this is y. So this is positive here, so we look at the positive side. So the square root 1 minus sine squared theta, and that's right here, this is 1 minus sine squared, but then we have this square root on top of it, so that just becomes, well, cosine theta. Cosine, oh, not theta, in this case we're using u, so cosine u times it by our cosine, yeah, cosine right here, u, and then du. So this equals to, simplifying it and putting these powers together, this r becomes r squared and taking it out of the integral, so r squared, now we have this cosine u times cosine u, that's just cosine squared of u du. And now again, if you recall my earlier video, I went over it a few days ago. Basically I showed, and you can see the video link below, I showed that the integral of cosine squared, we'll go x right here, just general, cosine squared of x dx is equal to 1/2 x plus sine of x cos of x, and then this is plus a constant c. And again, you can see the proof of this in my earlier video in the video link below. So if we use that, then we have, so thus we have the integral from the square root r squared minus x squared dx is equal to, then using this new variable, oh, this is r squared right there, forgot to square it. So we have this is r squared divided by 2, and then this is cosine squared of x is cosine squared of u, so we just replace it with u, so this becomes u plus sine of u cos of u, and then plus c, constant c right there. So now what we have to do is convert this back to the x variable, so convert back to x variable, and to do that, well, we use the substitution that we used. So we use the fact that x equals to a, in this case it's r sine theta, I mean sine u, not theta, because we chose, yeah, u right here. So if we switch this back, what this means right here, if we were solving for u initially here, what we could do is divide this by it, so we have sine u is equal to x over r, and then we have to take the inverse right here, so u is equal to arc sine or inverse sine of x over r right here. So remember my earlier video, you basically switch these, and this is going to be the sine on inverse trigonometric functions. So that's what u equals to. And now we have to find sine u and cosine u. Well, sine u is simply sine u equals x over r. Now we have to find cosine of u, and cosine of u, recall, this is equal to, like I showed before, opposite over hypotenuse. Hypotenuse, I think that's how you spell it. So if you were to graph this right angle triangle, this would be, this is u, opposite is x, hypotenuse is r, and now this one using Pythagoras, this is going to be, well, recall, I'll go over here, recall Pythagoras theorem, Pythagorean theorem or Pythagoras theorem. Basically, if you have a right angle triangle, this is, let's go a, b, c, basically c squared is equal to a squared plus b squared. So that's the basic one. I'll just put this in, hover this over. as a cloud. So then this part right here, this would be, well, if you were evaluating this, this would be if you separate it for one of the sides, you just move this over and then square root it. So this becomes r squared minus this side, x squared, all over square root. So that's the adjacent. So then we know that cosine theta, or cosine u in this case, is equal to adjacent over hypotenuse. Hypotenuse. Yeah, and apparently you spell it like this, U-S-E, and I think this is mixed that up. And hypotenuse is the r, so adjacent is going to be square root r squared minus x squared over adjacent, which is r. So we've solved this one here. This is cos u, and just highlight this over. So now we could plug in everything into here to get it back to the other variable. So what we have now is basically integral from, this is r squared minus x squared dx, and using the x variable, it's going to be equal to the integral. Let's go scroll back up here. R squared divided by 2. So we have, actually we're not putting the integral, so it's already evaluated. So r squared divided by 2. And then go back here. Then this is times it by u, which is going to be inverse sine of x over r. And then, so we'll just write that down. Sine inverse x over r. And then we have a plus sine of u, which is x over r. X over r, and then times it by cosine of u, which is right here. Cosine of u is r squared. Let's write this a bit neater. This is r squared minus x squared, and then bracket all plus constant c right there. And now if you were to simplify it further by multiplying this r squared into here, so we get equals to r squared over 2 times inverse sine of x over r, and then plus here this r. Whoops, forgot another thing here. So forgot divided by r there, so that's an r squared, and then this r squareds cancel. So we'll just have x times, and there's an x over 2, r squared minus x squared, and then at the end we just have a constant c. And now that we have this indefinite integral, we can evaluate the definite integral. That's from the integral. So evaluate the definite integral, or to get an exact number. And again, like I showed in my earlier videos on integrals, it's called indefinite because this constant c could be any number, so that means you don't have a definite answer or an exact answer. So evaluate the definite integral. So we have the integral from, or basically a2, or the area of that curved section, is equal to the integral from r cosine theta of up to r of square root r squared minus x squared dx, which equals 2. And now we're evaluating, well, this part, we can take this is the integral, so we'll evaluate it, and again we can get rid of that c, because the c's, when you subtract, they cancel. So take this 1/2 out, and we're evaluating this is the answer to that integral. So r squared sine inverse sine of x over r plus x. We've taken that 1/2 out. That's a constant across both sides. Then r squared minus x squared, and then this is we're evaluating it from r cosine theta to r. And again, the constant c gets out, doesn't affect anything. And when we evaluate this, so we have to go plug in the r. So plug that in, we have r squared sine, inverse sine. When you plug in r, we'll have r over r, which is just basically 1. Plus, now we have r right here, times it by r squared minus r squared. This just goes to 0. And then we have to subtract, now plugging this side in. So subtract, and then plug r squared So this is inverse sine like that. Well, actually, I'll put it down here to make some space. So subtracted by, this is going to be r squared sine, put the bracket like this, inverse sine x over r, which is going to be r cosine theta over r. This cancels, so we're just left with cosine theta. So the r's cancel, left cosine theta, plus now we have r cosine theta times it by r squared times r squared minus, this is going to be r squared cosine theta. And then put a bracket like that, so you're multiplying the 1/2 across all of it. Yeah, so now let's solve these parts individually. So this first one, we'll call this number 1. This one's 0, so we just can ignore that. Solve for this part, which is number 2. And then the last part right here, we'll call this 3. So in this number 1, the only thing that's different or that we need to solve is this. What is this sine, inverse sine of 1? So the first one, we have to evaluate what this is. So let's just say this equals to a number alpha right here. So what this inverse means is, if you were to rearrange it, this just means that sine of alpha is equal to 1. So this just means this is an angle. So when this inverse, that's an angle. When is it that angle? Then you'll have opposite over adjacent equals to 1. So if you recall like this, if you recall the function, let's go graph alpha up to y of sine right here. Sine just looks something like this, where at this point right here is pi over 2, and this curve is just sine, or y is equal to sine alpha. Yeah, and at this point right here, this value is 1, but also with the curve, it's periodic, so it goes back and forth. So you obviously have multiple 1 values, and it keeps going on and on. But in this case here, how we got to this point, this angle alpha, if we go all the way back up, basically we derived it from this part, where we had the variable u is equal to inverse sine of x over r. So then, in this one here, we defined u as basically between pi over 2 and 0. So also alpha is also within that. So the only range we could possibly have this sine alpha, this must be also following alpha is less than pi over 2, less than greater than equal to 0. Because this is the same one, it's just an alpha number. It's another number that could be the u as well. Use the variable, but now we have this part here. So it must be between here. So then this means alpha is equal to pi over 2. So alpha is equal to pi over 2, which equals to inverse sine of 1. So we have the first part right here. So we have this one. Now let's look at this number 2 part. And now when we have to solve for the second one, this inverse sine of cosine, so we have number 2 right here. We have to deal with this inverse sine of cosine theta, which equals to, well, let's say it equals to the angle beta right here, or this, so this beta looks like a b. So, and again, similar to this one, it has to be between 0 and pi over 2. So this is beta is less than equal to pi over 2, greater than equal to 0. Because this is just an angle within the variable u that we defined. And again, rearranging this is by definition the same thing as writing sine of beta is equal to cosine theta right here. So now we have to find a trig identity that relates sine and cosine. So if you recall how the graph looks like right here, this is let's go x and y. The graph of sine looks something like this. This is sine of x, or sine of x. Just draw this here, recall. So we have this graph, and then the graph of cosine is just shifted something like this. So it goes something like that, etc. keeps going on. So whenever there's a 1, this goes to 0. Whenever this is 0, this goes to a -1 or 1, etc. So it goes like that. And basically at this variable, I'll write this down. This is cosine of x. Yeah, and at this point right here, this is basically this is pi over 2. So what this means is basically we're just separating we're separate the tips here. I mean the tops. This is just separated by pi over 2 or shifted. So sine of x is just cos of x. That is so that cos of x is shifted. Yeah, shifted by pi over 2. Yeah, so now if it's shifted by pi over 2, this means that if we were to write this out, and also this is another trig identity that I went over in my earlier videos, you can see that below as well. So basically what we'll have is sine of x, I'll just erase this, so sine of x is equal to sine of, cosine, so it's shifted. So cosine, now we're shifting to the right, so we'll have x minus pi over 2. So this means that when you plug in pi over 2, and then basically you get back to the starting point of cosine 0. So that's basically the 0 point, or 0 point here is shifted over to this point by pi over 2. So to get to the 0, you need to put pi over 2. But also recall the trig identity that I went over in my earlier video as well, that you could also have cosine, well basically cosine of I'll just put x, and recall that cosine negative x is equal to cosine of x itself. So I'll put this in a bubble right here. So that means if we apply that, and then you can see the proof for this in my earlier video, but as you can see, cosine is symmetric so that the right side is the same as the left side. So the negative x or x is the same thing. So if we plug that in, cosine of negative x minus pi over 2, this could also equal to cosine of, and now we'll have this this be positive pi over 2 minus x. So you have two options here, and you can see that these are equal. Actually, I will show that they're equal. So basically, this means is we'll have to pick one of these, and I'll show you which one we'll pick soon. So for our case, we're looking at sine of b is equal to cosine of theta. So if we apply this above identity that we just derived there, or just explained a bit on it, so this could be written as cosine. So this would be the x. So that is our new x in this formula right there. So this is going to be cosine beta minus pi over 2, which also equals to cosine of pi over 2 minus x. So in this case, at when you have beta is equal to pi over 2, then what we have is sine of pi over 2, which equals 2. Well, sine of pi over 2 is just 1. I'll just put the 1 right here. So sine over pi over 2 is equal to 1, which also equals to cosine of, when you plug this in beta, you'll have, well, pi over 2 minus pi over 2 for both of these, which equals to cosine of 0, and cosine of 0 is also equal to 1. So as you can see, it's the same thing. That's equals to 1. But at beta is equal to 0, so when you plug in 0, what we have is basically sine of 0, which equals to, well, 0. Sine of 0 is just 0, which equals 2. If you were to plug this in now, will equal to cosine of 0 minus pi over 2, which equals to cosine of pi over 2 minus 0. And when you look at the graph here, at cosine is pi over 2, it's 0. At negative pi over 2, it's still 0, so it's still the right answer. And at sine of 0, that's 0 right there. So these are all equivalent, except what we have now is basically, so then this equals to, remove the 0, equals to, so basically sine of 0 is equal to, or 0 is equal to sine of 0 equals to cosine negative pi over 2 and equals to cosine of pi over 2. Except the problem here is because remember that sine beta is equal to cosine theta, and that this theta we've already defined as less than or equal to pi over 2 and greater than or equal to 0. So this is, we can't use this. Can't use this because it's outside of the domain. So we have to stick with this pi over 2 minus x. So we have to choose that, thus choose sine, so you have to use the identity sine theta equals to cosine, and then this is going to be pi over 2 minus beta, and then this equals to now, well, same thing, cosine theta, so because these two are equal. So we have to choose this because again, trigonometric functions they are periodic, so you could always have many different answers, but since we're restricted on the domain, we have to pick this one. So this means that this cosine here, this equals to theta. This is just theta. It's the same thing. If cosine pi over 2 minus beta equals theta, this means that pi over 2 minus beta equals to theta right here. And if we rearrange this, we get beta is equal to, move this over, move this out of there. Beta is equal to pi over 2 minus theta, and beta is equal to, finally, is just equal to this inverse sine cosine theta, which was we were trying to solve, which equals to inverse sine cosine theta. So there is our part 2, and now we just need to look at part 3, which is the last one. Scroll all the way back here. We have this right here, this r cosine theta, r squared minus r squared theta. Well, what we can do is basically just use what we already applied before. So this was a cosine in there. So going back here, we have number 3. This is r cosine theta square root r squared minus r squared cosine theta squared. I believe I squared it here. I forgot to square it. Yeah, because when we had to square that, so I forgot to square it there. So going all the way back here, factor this out. This is this r cosine theta times it by square root r squared times square root 1 minus, take that out, cosine squared theta, and like I showed above, basically the square root 1 minus cosine squared theta, this whole thing is equal to, well, this one here is equal to r squared, square root is r, and this is just equal to sine theta, and then the square root gets cancelled, because you have sine squared and square root just cancels. So what we have now is equal to r and then r squared cosine, so this is the r, then there's an r squared cosine theta times sine theta. So that's what this third part is, and then what we have now finally is just, we could put these all together. Just going back all the way up here. Let's see, where is it? It's all the way over here. So now put this all together, this whole thing. We have A2, it's back here. Thus A2 is equal to, scroll back up here. So A2 is equal to square root r cosine theta to the r squared minus x squared. So we'll have this 1/2. I'll just write this down for completeness sake. R cosine theta to r square root r squared minus, this is x squared, and then dx, this equals to 1/2, going back up. So 1/2, this is r squared times inverse sine of 1, which equals to basically this theta, which we solved as pi over 2. So this is pi over 2, and this goes to 0. So we have r squared times pi over 2 plus 0. That's the cancellation. And then we have to subtract this one right here, r squared times inverse sine theta times cos theta, which equals 2, which I showed here, which is just this beta sign, which is pi over 2 minus theta. So we have a minus, and then what was that again? So we have this pi over 2 minus theta, put in bracket, and again, what was that multiplied by? Forgot. Scroll back, so r squared. And then this last part here, r cosine, which is actually just, actually what is this, r as well? Let me just go back. So that's just r squared. And then we have to the last part is just this whole thing. So r squared, and then plus, I'll just write it here, plus r squared cosine, I'll put the sign in front because it's more common, sine squared, sine theta cos theta, and then now we just put in bracket, and then all like that over bracket. So this equals 2, multiply this inside. So what we have is 1/2, this is going to be r squared times pi over, well, 4, plus 0 is gone, multiply this inside, negative, multiply this out, so 1/2 r squared is going to be r squared times pi over 2 minus r squared theta, and then plus r squared sine theta cos theta, and I'll just multiply this 1/2 inside. So I'll erase this, make this a negative, and basically multiply by 2. Actually, that's a bit confusing. I'll just do this on the next step. So we have r squared pi over 4, and let's multiply this inside. So we have negative 1 over 4 r squared pi. This is the same thing as here. This cancels. So this goes to, well, goes to 0. They just cancel the same thing. R squared pi over 4. So, and then multiply here. So we have plus 1/2 r squared theta, and then the last part is minus 1/2 r squared sine theta cos theta. And that's it right there. So this cancels, so this equals 2 1/2 r squared theta minus 1/2 r squared sine theta cos theta, and this is our area 2 right here. And also what we realize here, this 1/2 r squared sine theta cos theta, if we scroll all the way back up, what we actually find out is, let's just go back up here. That's the first thing we solve. This is a1, r squared divided by 2 sine theta cos theta. So that is our a1 actually. So what we could do is scroll all the way back. This equals to a1. So what we have is a2 is equal to 1/2 r squared theta minus a1. And thus finally what we have is basically the total. Thus area A is equal, of the sector is equal to a1 plus a2, which equals 2, well, a1, I don't even need to write it, plus 1/2 r squared minus a1, so that's our a2, and the a1's just cancel, so this just equals 2 1/2 r squared theta. Yeah, and there's our proof. Well, for theta is less than equal to, this is for theta is less than equal to pi over 2 greater than equal to 0, but this works for, but this still works for all, I'll just write, but this works for theta is less than equal to pi, 2 pi greater than equal to 0. So it still works for here, and then the proof for that is basically, well, for example, if we look at if we look at where theta is, well, greater than, let's say it's greater than or equal to, I'll just write greater than pi over 2, but less than or equal to, put that there, pi. So for example, in this case, we'll have something that looks like this. Let's say if we have a sector like this. This is our theta. So if this is our theta, if we break this up, what we actually have is, this is pi over 2, that's just 90 degrees. And then this this part right here, let's call this, we'll just call this alpha. So we'll prove that the area is still A equals 1/2 theta r squared. So for the first section, this is area 1. We'll just shade this. This is area 1. This is area 2. So what we have is, and in area 2 you could use the formula. So for both of them we'll have areas equal to A1 plus A2, and A1 is simply, well, just apply the formula we solved for the sector where theta is equal to pi over 2. So we'll have this equals to 1/2 r squared, and this is r squared times by pi over 2. And then we just add, now we add this theta, this alpha there. So this is a separate sector, so that's equals to 1/2 r squared times by alpha. And as you can see, what this means is if we just factor out this 1/2 r squared, 1/2 r squared, this is just pi over 2 plus alpha. And in this case here, theta here, recall that theta, let's put this here, theta is just simply the addition of the two. So theta is equal to alpha plus pi over 2. So this is just theta. So this means that the area is equal to 1/2 r squared theta. So there you go, it's the same thing. Yeah, and likewise you can do the exact same thing for the third quadrant. So if you have, if you have the area something like this, so let's say this is our new theta, so we could apply this same thing. So in this case we will consider this part right here as theta, and in this case we've proved it already, that's correct. And this one is just our new alpha. So then the area is equal to, again, the summation of the two, and where this theta is equal to pi plus alpha. So this is 1/2 r squared. This is r squared times it by, so the first one, pi plus 1/2. So this is just for completeness sake, as you can see the pattern. R squared and then times the other one, alpha. So that's just its own sector that we proved, which is less than pi over 2. So again, factor this out, 1/2 r squared, pi plus alpha. So this equals to 1/2 r squared theta right there. And that's the area. So it's the exact same thing in the last, for completeness sake. Lastly, if we have a sector that is like this, let me just draw this a better circle, like that, where up to this point, so in this case, so also I'll write this theta is, let's say, less than, let's say it's greater than or equal to pi, but less than or equal to 3/2 pi. So that's 3/2 is over at this side like that. And that is just, what is that, 275? 260 degrees, I think. Actually, that's 270 degrees. This is 270 degrees. Add another 90, then you're gonna get, yeah, 360. So that's about 270 degrees. That is 270. So now this last one's exact same principle. This is theta, and then up to here is 3 pi over 2, and then this last one is alpha right here. So just use alpha, just again for completeness sake. Alpha, and then area is equal to 1/2, and where again theta is equal to the addition of the two, 3/2 pi plus alpha. So we have this part right here, r squared, where this is r, and then 3 pi over 2 plus 1 over 2 r squared times it by alpha. And again, this is the same thing when you add them up or factor it out. This is r squared 3 over 2 pi plus theta, which is just equals to theta. So this is just equals to 1/2 r squared theta. So as you can see, it works for all the quadrants, and we've just proven it. So thus a equals to 1/2 r squared theta for theta is less than equal to, well, 2 pi greater than equal to 0. So basically for any angle in the circle. And there's our proof for it. It's a pretty extensive proof, and yeah, just hopefully you were able to follow along. A lot of trig identities, a lot of just talking about this, making sure we pick the right one. If we used a different one right here, if we used beta minus pi over 2, we'll get a negative answer because it's the way this works. And also I used, in the very beginning, I used the substitution x equals r sine theta. And in fact, if we used x equals r cos u, actually not theta, so u would have been actually much simpler to solve. I just wanted to use this because it was pretty intense and it shows some next level mathematics. Anyways, that's all for today. If you learned from this pretty extensive proof video, and like always, you could download these exact notes in the link below.